Okay, let's get started. So this is already the last lecture before the recess week, and I have some announcements to make. So when we return after the recess week, as you know, we have the midterm, and the next lecture slot, that's on March 3. And logistics have been uploaded to Luminous yesterday, so I hope you got the email notification. So please read that carefully. So in terms of tutorials, so this lecture's content, right, because next week is recess week and we don't want to wait until the week after because midterm is coming up. So we will release the video tutorial for that during the recess week. So that's gonna be done on Monday. And then for week 7 tutorial, so that's midterm week, and there it's going to be kind of free in terms of so tutors can go over any material that they like or turn their sessions into consultation sessions. So I'll leave it to individual tutors to do what they want, and they'll announce that to you. And for that, no attendance will be taken. And then for the week after midterm, because we've been releasing these video tutorials like for recess week and for Chinese New Year week. So to make up for that, we'll cancel the tutorial the week after midterm. So that's week 8. And then for the rest of the semester, from week 9 onwards, we'll be back to normal all the way to week 13. So these should be the only exceptions, the only announcements that need to be made. Okay, more announcements. So I'll upload a practice midterm by Monday of this coming week to give you time to practice before the actual midterm. And in order to go over solutions for that practice midterm, so there will be a review session run by 2 of our TAs on Friday. That's February 25th, and that's going to be on Zoom. So we'll send out an email invitation. And then, so our TA Christian also going to post some extra practice problems under supplementary materials. Again, so email notification is going to come up. And yeah, so also there will be a programming assignment. This is optional, as announced at the beginning of this semester. This you can make up some points in the continuous assessment component, and that will be posted soon. Should be in the next few days, and will be due on Sunday, March 6th. So that's the Sunday after the midterm. And the content of that assignment will also be on the material that's going to be covered in this lecture. And finally, I've released a mid-semester survey that's under a survey on Luminous, and it's anonymous. So it's just one free text response. You can tell me any comments, any suggestions, anything about the module so far, and I'll look at that and then think about what adjustments could be made for the rest of the semester. So I'll leave that open until next Friday. Okay, so any questions about logistics that I can answer for you right now? Okay, everything clear? Good. Okay, then let's get started with the content of today's lecture. And today's lecture is the continuation of last week's lecture on hashing. So we'll see two more applications of hashing. And so before that, so last week we talked about hash tables, right? And we said that, okay, like if m, so the size of the hash table, if we choose it to be roughly on the order of the size of the or the number of inserted items or the number of operations that you need to make, then that would be good enough in the sense that each operation, like add, delete, or query, will take a constant time, so big O of 1 in expectation. Now, one of you asked, okay, like then if we know this m in advance, then great, like you can choose m accordingly. But in reality, right? So you don't know n in advance. Say like how many IP addresses you're going to have to deal with, or like how many student IDs you're going to have to like deal with for a particular module. Then how do you set up? So this is of course a very reasonable question, and the way that we do that is what's known as rehashing. And the idea here is that if n is too large, right? Suppose like at the beginning you think n is going to be 100, so you choose m maybe like 200. Something like that, but then n grows too large and becomes 500. What do you do? So what you do is you choose a new hash function for a larger M. So you expand the hash table. Now, of course, once you expand the hash table, this is a very costly step, right? Because you have to rehash all elements, because now you have a new hash function. All the work that you've done is lost. You have to rehash everything in the old table according to the new hash function. And this is very costly. But there's the idea that we're going to come back after midterm. It's called the amortized analysis. And the idea is that even though the rehashing step is costly, but it happens really infrequently. Right? Suppose you think about like you rehash every time the size is like twice what the size of the hash table before, something like that, then it grows in power of 2, then this rehashing step is going to happen quite infrequently. And even though each rehashing step is costly, you can amortize it or like average it with the other steps which are like inexpensive. So that on average, like or in total, the cost of each operation is still not going to be that bad. Even though like for one operation, if it's the unlucky operation, right where like right where the table needs to be expanded, right where you need to do the rehashing, that's going to be very expensive. But on average, when you talk about like many operations together, then it's going to be okay like per operation. So that's the idea. But yeah, we're going to revisit that after the midterm. So don't worry about that for now. Okay. Variable sized arrays. Yeah, I mean, you can, yeah, variable size array is kind of another variant of this kind of idea. Okay, so first we're going to talk about the application of string pattern matching. So the setting here is that you have a text string. So that's usually a very long string, like this we call it T of length n. For example, these could be like all strings in your emails, right? The text in all your emails. And then you have a usually shorter, much shorter pattern string P, which is of length M. For example, it could be CS3230. We want to search for that in the text string. So the question is, does the pattern string P occur as a substring of the text string T, right? As you can imagine, like this has many applications, like search engines, plagiarism, DNA sequencing. This is another important one, right? We have a sequence of DNA if we want to find whether it appears in this genome or not. This is also an application of string pattern matching. So how can we do that quickly? Right, and in this lecture, we're going to assume that the strings are in binary. So it's just like all the strings are in 0, 1 in bits. But this idea can be generalized to any alphabet, right? Even if you have like ABC, that is just like kind of a base 26. And yeah, anything kind of, as we talked before, kind of any kind of input can be converted to numbers. Okay, so so the first solution, like well, when you have a problem, you can think about, okay, first of all, like, what's the most simple solution? What's the easiest, most straightforward solution that you can think of? Right, for this problem, for string matching, there's going to be this algorithm. So what it does is just we want to find whether P occurs as a substring of T or not. Right, so you just check all possible locations. Right, you have this N and M, and you have the outer for loop that iterates over the possible positions of the text string T. And then you check whether this pattern string P matches with that position or not. Right, so when S equals 0, this is T position from 1 through M. And then if it occurs, okay, print that out. If not, move on to the next position. There's going to be positions from 2 to M plus 1. Check whether it matches or not, and so on. Right. Okay. So what's the time complexity? What's the running time of this algorithm in terms of M and N? Yeah, so it's going to be roughly order n times m, right? That's because in the outer loop, you run from 0 through n minus m, so that's like n minus m times. And then in the inner loop, or in the if statement, right? So that for each if statement, you need to check whether two strings match or not. And in the worst case, you need to check up to m positions. So that's going to be n times m. And you can see if m is large, right? If m is small, then that's fine. If m is like say 3 and n is like very large, that's still kind of not too bad. That's going to be like 3 times n. But if m is large, say m is n over 3, then this is going to be n squared, right? Because n minus m is going to be 2n over 3, and then m itself is going to be n over 3, and so on. Yeah, so in the comment, yeah, there's a very good point about skipping this mismatch, right? I mean, you can think about, okay, like say you want to have to do this check, right, whether it matches or not, and maybe even in the first position it doesn't match already, and then you can stop the check immediately, right? Because if the first position of p and the first position of t that you're checking doesn't even match, then you can just stop checking. But actually, you can construct kind of bad examples where the running time is still going to be bad, kind of examples that fool the algorithm in the sense that the algorithm has to keep checking until the latter positions, and then the running time is still going to be high. Yes, comment formally define big data in terms of, yeah, I mean, don't worry about that too much. I mean, yeah, we're not yeah. So I mean, running time here, like say it's order n times m. I mean, yeah, that's fine. I mean, I'm not going to go into about how we define a big data for more than one variables. So the question here is, okay, right? In this case, can we do better, right? If m is large, we don't want to spend time n squared, and we're going to come back to the idea of what if we use randomization? So that's the idea that we've been using in the past 2 lectures. Right? So first with the quick sort, like randomizing the pivot, and then last lecture with hashing. So I'm choosing hash function from a universal family of hash function in order to ensure that collisions happen only rarely. Right? Adversary cannot choose the input so that it collide the inputs, the hash functions of the inputs collide all the time. So yeah, so the idea here is due to Hart and Robin, so two very well-known computer scientists, and there are 2 ideas that are going to be involved here. So first is the faster checking of the string equality, and the second idea is rolling hash. Okay, so for the first idea, so in order to check, we said that in order to check whether the pattern matches with the substring of t of length m or not, right, we go through like each position one by one. That takes the time order m. So that's kind of too long, right? In order to speed that up, we can use a hash function, right? So why not just hash both p and the substring x of t, and then check whether the hash functions are the same or not. So we'll design the hash function so that it outputs only a small number. I mean, if it outputs kind of the same thing as before, then that's not going to be useful. Just outputting the same as the input. So it'd be idea of hash tables, we restrict the range of the output. Right? So we're going to choose h that does that, and so that the arithmetic can be done on these hashes in constant time. And so if we have that, then runtime for the equality check, we have the right. If we have this hash function h, then we have to hash the pattern p. Right. Then we also have to hash the substring x of the text t that we're going to test against, and then we have to spend time order 1, so constant time, in order to compare these 2 strings or these two hashes, whether they're equal or not. So the total runtime for pattern matching is going to be, so first of all, we have to hash p, right? But you just do that once. You don't have to keep doing it. But then, in order to check the hash of each substring of t, you have to do that one at a time, right? So you still have to do that how many times? So that's still like n minus m plus 1. And for each time, you have to hash this string x, and then you have to spend order 1 time to compare whether the hash of x is equal to the hash of p or not. Right? So that's still bad because there's still n minus m plus 1 term, and then in order to hash each substring x, you already need to spend time m, right? Because just reading the string x itself, x has length m, so reading the string x itself also has time m. So this is not an improvement to what the naive algorithm does. So the other idea, right, that will make this work and make this algorithm faster is that of rolling hash. And the idea here is that you think about it, right? So the first substring of t that we're testing is from 1 to m. The next substring is from 2 to m plus 1, I mean, these substrings are so similar. They overlap in like almost the whole substring, right? They just change in one position, like position just move over to the right by one position. So what we want to do is we want to design the hash function so that we can update the hash of one string from the other quickly. Right? So in particular, we have the hash of the string from positions 1 through m. We want to update to the hash of the string from position 2 to m plus 1 in constant time, instead of having to look at the string from 2 to m plus 1 and then like just rehashing it. Right? So we want to do this quickly. And more generally, we want to do this quickly for every pair. Every time we move like one step to the right, we don't want to spend time m to like inspect the whole string and then like hash the whole string from scratch. Instead, we want to update from the hash that we already knew from the previous string, right? One position to the left. So if we can do that, right, suppose that there's a hash function h that allows us to do this, then the total runtime for pattern matching is now going to be, so again, we have to hash pattern p. We also have to hash the string from position 1 through m, like that's the initial string, right? That we do have to spend time m. But then after that, right, every time we move one position to the right, then because we only take time order of 1 to compute the hash of the new substring of length m, and also time order 1 to compare this the hash of the string with the hash of p, then the total running time is going to be order of m plus n, right? Because the first two terms are order m, and the last term is like order n minus m plus 1. That's no more than order n, so it's n going to be no more than order m plus n. So in the comments, so hash each character separately. So yeah, that doesn't, in this case, like each character is just 0 or 1. Remember, we're assuming that each character is very binary. So each character is 0 or 1. So it doesn't make sense to hash each character separately because there are going to be just two possible hashes. Here we're interested in the whole substrings of length m, like what that hashes to. Okay, so yeah, we're interested in that the two substrings have to match exactly. Okay, so yeah, so here this is the runtime if we have such a hash function h, right? But then like what is such a good hash function h? And note that here we cannot just choose like any universal hash family, because it's not going to, even though it guarantees this low collision probability, but it's not going to, it's not designed so that we can update one hash from the other quickly, like from these positions like 1 through m to like 2 through m plus 1. So the hash function has to be chosen specifically for this purpose. And yeah, what's going to work here is what's known as the division hash. So the idea of the hash function itself is actually very simple. So what we do is we choose a prime number, which is a random prime number in the range from 1 to k, where k is going to be some large number that we'll choose later. And there's a known fact that the number of primes in the range 1 through k, right, for any k, number of primes in this range is going to be more than k over natural log of k. So this is saying that you take any range of the first k positive integers, then the number of primes is kind of large, right? It's 1 over log k, like ratio or fraction of the whole set. So you can choose a random prime number, and then you define for any integer x, right? But you have this p. You have defined any integer x. Its hash is going to be just x mod p. So just take the remainder when dividing x by p. Okay, and so note that if p is small, p is relatively small, and then x is say b bits long in binary, then hashing is going to take order of b times. So we do this division and then find the remainder. And what we want to show is that this hash family is good, right? I mean, we want to show that it helps prevent collision, so that it's approximately universal, right? We want to show that not too many elements x and y are going to collide when dividing by mod p when we choose p randomly. And again, like if we fix like p in advance, then the adversary can just like choose x, y, z, and like other inputs so that it all like have the same remainder when dividing by p. Right? But the idea of this hash family is that because p is not fixed in advance, p is chosen randomly from this range 1 through k, then this hash family is going to be approximately universal, and so the expected time is going to be low for performing queries. Okay, so yeah, but there's one thing to notice that so note that you might wonder, okay, how do you choose a random prime number in the range from 1 to k? So the way you can do that is first you just pick a number from 1 to k uniformly at random, right? And then you test whether that number is prime or not. If it's not, you just pick again. Okay. And so note that this should kind of ring a bell, right? Keeping doing something like at random until it works. So that we've seen this idea a couple of times already with it's what's known as geometric random variables. And remember that if the probability of success is q, then in expectation you're going to be doing this for just 1 over q times. And here, so what's the expected probability of success? Right? So suppose that you choose a random number from the range 1 to k, then the number of because the number of prompts in this range is more than k over log k, then the expected or the probability of success is going to be so probability that the number of that you pick, so probability that number of you pick, say let's call it y is prime, y is picked randomly from the range 1 to k. So this is going to be at least 1 over log k, right? Because the number of prompts is at least k over log k. So this means that if you keep picking randomly and then checking whether a number is prime or not, you're not going to have to do more than in expectation log of k times. So that's a relatively low number of times that you need to pick. And remember, like checking prime number, so that can also be done efficiently. It's okay. So yeah, that's our goal. So the idea is that we want to show that this family is good and works for our purpose of both being a approximately universal hash family and also allow us to do this rolling hash quickly. Okay, so first we want to analyze the probability of collision, right? So suppose x and y are different, what's the probability that their hashes collide? So we suppose that x and y are numbers of at most 2 to the b, so they can be written in b bits, right? So this b is our applications b is roughly m, right? Because we're hashing strings of length m, so binary strings of length m. So this claim is saying that the probability that their hashes collide is less than b times log k over k. So this k is k is, you can think of like roughly p, right? Because p is chosen from the range of 1 to k. So if you want it to be universal, remember this probability is going to have to be something like 1 over k, right? Because if we are hashing into a kind of 1 over p or 1 over k, that kind of number. But here it's slightly more, right? So there's a log k in the numerator, and then also this b. So it's a bit more. So it's not quite universal, but it's also pretty close. Okay, so why is this true? Right? Why is it true for this division hash function that the probability of collision is low? So okay, again, we look at what does it mean when the hashes collide. So that means that if we look at the difference, right, that z equals y minus x, then yeah, z is going to have to be 0 mod p, right? So that means that p divides the difference, right, y minus x, and also a number that is less than 2 to the b. That's going to have at most b distinct prime factors, right? So why is that? Suppose suppose for contradiction that it has more than b distinct prime factors, then it would have to be at least what? It has to be at least so 2, right? It's like the first b prime numbers, 2 times 3 times 5 times 7, and so on, like b times. and then that is at least 2 times 2. Every number is at least 2, right? So b times, which is 2 to the b. So if z has more than b prime factors, it's going to be has to be at least 2 to the b. But we know that it's less than 2 to the b, so it can have at most b distinct prime factors. Okay, so that's saying that it doesn't have too many prime factors, but we know that in order for the hashes to collide, p must be one of the prime factors of b, right? Because that's what y minus x equals 0 mod p is saying. So this tells us that the probability that the collision happens is going to be no more than b over k over log k, right? And that's because the number of primes in the range from 1 to k that you're picking from is that from the fact of the previous slide, that's at least k over log k, and that the number of primes that make the collision happen is at most b, right? So you're picking from a set of size at least k over log k, and then the kind of bad events, the bad numbers are only at most b of them. So the probability that the collision happens is at most b over k over log k, which is flip the fraction. That's going to be exactly b times log k over k, as in the claim. In the comments, so can we improve this to around b over log b? Yeah, I mean, okay, so this right. So here you notice that we're saying like 2 times 3 times 5 times 7. So I mean, this kind of and then we're saying that each number is at least 2. So indeed, if you like kind of do this bound more carefully, then you could get a slightly better bound. But yeah, it's not going to be much better. Also, it relies on some facts from number theory. So this 2 to the b bound is good enough for our purpose for this analysis, showing that this hash function is good. Okay, so yeah, this claim is saying that the probability of collision is small, right? And then okay, so suppose like we really want to do this, right? This equality check. So we suppose say like m is a million. Maybe this pattern string is also pretty long, but maybe the text string itself could be like 100 million. Then so if you do a naive equality check, so that would take order m time, right? Let's check every position of the string. But what you can do using this hash family is you can set k. So remember, k is this number here, which is the number of you choose prime p from the range of 1 through k. Remember, I said the k will be chosen to be a large number, right? So we choose k to be say like 100 million. And from the claim in the previous slide, we're going to have that the probability of collision, right, between the substring x and the pattern string p is going to be, so it was b times log k over k, right? So b, as I said, is like m, right? Because it's that's what is being hashed. It's length is m, so that's million. That's 10 to the 6. And then the term log k over k, because k is 100 million, log k over k is going to be roughly this number, so 19 over 10 to the 8. And you calculate it, it's going to be less than 1 over 5. So the probability of collision is going to be less than 0.2. Okay, so in the comment, the number of bits is a million. Yeah. So exactly. So this is saying m is a million, saying that this pattern string is of length a million. Yeah. And as I said, like the text string itself could be like much longer. Maybe like you're looking at the text string of size, say it's 100 million. And yeah, so note that this idea that we've talked about before, that even though like these numbers are large, right? So k is large, but the hashes themselves are small, right? Because if say k is as long as k is no more than 2 to the 32, then the hash these hashes can be length no more than 32, and so they can be stored in one machine word. And by that, with that, we can assume that they can be compared in constant time. Yeah, so 19 is the natural log of 10 to the 8. yeah, indeed, 1/5 is still high, and we can improve this if we choose k to be even larger. So yeah, this kind of illustrate you that if k is 100 million, this bound gives you like this no more than 1/5. Choose k to be even larger because this here is b times log k over k, right? We choose k to be even larger, then the bound of probability bound is going to be even smaller. Yeah, so k is the size of kind of because it's this p is drawn from the family 1 through k. So the size of the hash set is p, which could be anywhere between 1 and k. So the kind of the size of the hash set itself is random. We don't know in advance kind of what it's going to be. Okay, so okay, so question: how does this fulfill the condition of universal family of hash 1/5? So here we're not showing that it's universal. As I said, it's so this equality here, v log k over k, is showing that's roughly universal. For universal, we'll need something like 1/k. Here there's a b log k, and here so on this slide we're doing like explicit numbers just to give you an idea of like how this bound works. But yeah, 1/5 is not something not a good bound, as someone has already pointed out. And yes, also yeah, not like not what we're going to aim at. And yeah, let me get to the next slide because this is what we can aim at. So we can aim at the probability of getting a false positive being less than 1%. So remember, false positive, so that's something is showing up to be positive, but it's actually not. Right. So one thing, you should notice with this algorithm is that there's never going to be a false negative. Right. Remember, false negative when like it says no, but then actually it matches. So if the hashes are different, then for sure like the x and p are not equal. Right? If the h of x, right, so let me write down, so h of x is not equal to h of p, right? Then yeah, definitely x is not equal to p, right? And so this is saying no false negative. But if h of x is equal to h of p, then it could be, we cannot say, right? It could be that it's a false positive. It could be that x could be either x equal p, right? They're really equal, or maybe they're not equal, but their hashes happen to be equal. So there could be a false positive. And our goal to bound the to upper bound the probability that there's a false positive. So if the hashes are the same, we want to show that okay, like the probability that they're actually the same is high. So question, we're multiplying by m, are we hashing? I think you're talking about this with this k. If it's with this k, then the multiplication by m in this term is it's going to come up in this analysis. So it's going to be sure that you'll see in the analysis. If we really want to ensure false positive, it's a good idea to verify x and p. I mean, if you do equality check right directly, then I mean, if you do just check the strings, then that's going to take time order of m, right, which is too much. That's why we're doing a hash function. And you see that even with this one hash function, we can bound the probability of false positive to be pretty low already. Yeah, so 1/5 of the time, that was from the analysis of the previous slide. So as I said, like if we increase k, so we change k to be 1,000, right, a billion, right, then this probability is going to be lower. So don't dwell on this 1/5 too much. Just you only check once. Yeah, I mean here you only check once. So indeed, like if you want you want to be like reduce the probability, you can like make k larger. You can like add other hash functions. So there are other ways, but of course, you have to pay the price of a higher running time. So this is to show you that, for example, like in this slide, instead of 20% false positive, we want to get 1% false positive. Right. So what do we do? What we do is we choose k is to be this quantity. This false probability means that the algorithm may give wrong results. Yeah, exactly. So that's kind of right. Okay. So I guess this is not something that we've seen with for example, the quicksort, right? So quicksort, I mean, it's the result is always right, but the time that the algorithm takes can be too much. Whereas here with equality check, then it could be that the algorithm can give wrong results, and we're going to live with that. So these are like two different types of randomized algorithms that I mentioned briefly in lecture 4. Yeah, I mean, if you really want to be sure of correctness, you can pay the price in terms of running time. So the hashes come out to be the same. You spend the time to check whether like these strings are the same or not. Yeah, how viable is trying to use another hash function? I mean, I think a better way would be just to increase k, because you want to reduce the probability of getting a false positive. You increase k immediately. This probability is going to be lower. And yeah, with about this like correctness or like wrong answer issue, like you might remember this discussion about Las Vegas and Monte Carlo algorithms. Right? So Las Vegas is the algorithm is always correct, but then like running time could be bad. But here we're dealing with the Monte Carlo algorithm. The algorithm could be wrong, but the running time is going to be bounded. But I mean, yeah, you don't need to remember like which is which. Okay, yeah, I think I'll move on, and then I can answer other questions at the end. Okay, so with this analysis, okay, we choose this k to be by this quantity, right, 200 mn times the log of 200 mn, and we look at what's the probability that we get a collision, right? So this again we use an indicator random variable like e sub I be the event that the string from positions I plus 1 through I plus m. And p, the pattern p, are unequal, but they have the same hash. This is a false positive. Right? So this probability by the claim, right? The claim was what was it? B log k over k, right? So this is b log k over k is this going to be this term here? So m times log of k over k, and then we plug in k. You see that these m's cancel, and you can pull out the 200 n, right? So this is the 1 over 200 n term, and then inside what you have on the top like log 200 mn log 200 mn. So this term is this log 200 mn plus log 200 mn, right? So that's why you get this term here, because at the numerator you have just log 200 mn, so that's to be 1 and then plus this fraction like log over log, and yeah, because this fraction here, the log is less than log, right? As long as the number inside is greater than 1, like taking log twice is going to be give you a smaller number than taking the log once, so this is less than 1, and that's why you have this ends up being at most 1 over 100n. But this is just the probability that there's a collision at the position in the substring from position I plus 1 through I plus m. Right? Then like there are many substrings that we're checking. In particular, how many are we checking? That's order n, right? Because that's the length of the text string. So in order to bound the probability that there's a false positive at any position, then we have to use this union bound, right? So a probability that at least one bad event happened, right? That's the probability of union of EI. is going to be at most the sum of the individual probabilities. So if you haven't heard of a union bound, so this is a statement that says that, like, if you have say, two events, right, then the probability that at least one of them happen is going to be at most kind of the sum of like the probability that each individual event happens. So probably say E1 or E2 happens, it's going to be bounded above by probability that E1 happens plus probability that E2 happens. And this doesn't depend on whether E1 and E2 are dependent or not, right, or independent or not. Doesn't need that assumption. I mean, you can look at it as a Venn diagram. Let's say this E1, this is E2, and probably that E1 or E2 happens. That's the whole area, right? And then the probability that E1 happens, so that's going to be the first circle, and then probably that E2 happens, it's going to be the second circle. Right? So you can see that just by adding up the area, that probably that E1 union E2, right, or E1 or E2, that's always going to be at most each probably adding up separately. And it's going to be an equality if these two circles are disjoint, right, if E1 and E2 are disjoint. Yeah, I mean, you can do different things, right, in the comments. So you can increase k, like run the same algorithm like more than once. If you check the exact value, then still, I mean, you can only check this when the hashes come out to be the same. Right? It doesn't completely defeat the purpose because you don't have to check this every time. Right? If the hash values are different, then you know immediately that the strings are different. So you're only restricting to just yeah. Okay, so what's the running time for this equality check? So if k is right, k is this yeah, I think this has to be 200. 200 mn, then any prime that at most k, right, can be stored as a bit string of length log k. Yeah, so the point here is that log k is going to be roughly m is at most n, so it's going to be order log n. Right, then again, like the idea here is even though k is large, log k is relatively small. So we can assume that the order of log n bits fit in a constant number of machine words. And this allows us to check this quality of hashes in constant time. So now, okay, we have this equality check, but then we haven't talked about the second part. Right? So how does this hash function allow us to update from one hash to another quickly? Right. So yeah, this is the idea of rolling hash, and as you can see in this figure, right? So suppose like we're looking at a string from 1 through m, and then 2 to m plus 1, but the idea is the same, like for any two adjacent substrings of length m, right? Then if x and x prime are the binary numbers, so we interpret these strings of length m as like binary numbers. And the first one could be like 1 0 0 1 1, maybe like m equals 5. This is a binary number, kind of, yeah, what number is this? 2 to the 4 plus 2 to the 1 plus 2 to the 0. That's 16, 18, so 19, right? And then maybe the next bit is 0. So you look at this substring. So what number does that correspond? So that's going to be 2 to the 2 plus 2 to the 1. So that's going to be 6. Right, so that is how we interpret the binary. So yeah, you can see that so x is can be written as this the sum, right? So ti is like just 1 or 0, and then times 2 to the m minus I, and then similarly x prime just like we move one position to the right, so it's ti plus 1, and then again times 2 to the m minus I. Yeah, for example, if we're looking at this text, right? So say like the whole text is length 3, and then m equals 2, Then we look at the first string, that x, that's x, and that's 2 times a1 plus a2. And then the next string is x prime, that's 2 times a2 plus a3. So you can roll, like you can move from x to x prime by just changing a little bit. I mean, yeah, these strings are so short that this example might seem strange, but yeah, the idea applies even if you have longer strings. Right? So even if say m equals 4, then so say x is it's going to be like 8a1 plus 4a2 plus 3a3 plus 2a3 plus a4, and then x prime is what? It's going to be moved one position to the right. Right? So it's going to be like 8a2 plus 2 plus 4a3 plus 4a3 plus 2a4 plus a5, right? And then you can see that these two strings are quite similar, because x prime is what is 2 times x, right? And then once you multiply x by 2, then you can minus minus 16a1, and then you add a5. Right? So instead of having to compute the x prime from scratch, it's just this small difference, minus 16a1 and then plus a5. So this allows you to get from x to x prime quickly. But then, okay, that's from x to x prime, right? So this is the formula. So what about their hashes? Right? What about they're getting from the hash of x to the hash of x prime? Well, so that's the great thing about the division hash, right? Because division is can be distributed into this modulo function can be distributed into both addition and multiplication. So remember that two numbers like a and b, then you have like a plus b mod p, or even that doesn't even have to be a prime number, like mod any number, that's going to be equal to a mod p, then plus b mod p, and then you mod p the whole thing, right? So this like distributing mod p into addition. And similarly for multiplication, you have a times b mod p, that's a mod p times b mod p, and then the whole thing mod p. Okay, so yeah, that's why with this we get from x to x prime quickly. But yeah, not only that, we can also get from the hash of x to the hash of x prime quickly. That's because the hashing, what it does is just doing mod p, right? So you get that the hash of x prime is going to be twice of the hash of x, and then minus you follow the formula to get from x to x prime, right? It gives you a t of 1, so the first position of the text string, times the hash of 2 to the m, and then plus position m minus 1 of the text string, and then everything here, you mod p, right? So this is how you get from the hash of x to the hash of x prime. So note that you just multiply it by 2, you minus this t1 is just a bit, and then hp by the hash of 2 to m. I mean, this is used like every time you update from x to x prime, like from any position in the text string. Right? So this hash of 2 to the m, you can just compute in advance at the beginning just once, and then use it every time you do this update. And the t of m plus 1, this is again just 1 bit, and then this is also just 1 bit, so 0 or 1. So you can see that you can update from x to x prime in constant time, right? Because what you do is you already have hash of x times 2, and then you do this plus and minus calculations. Okay, yeah. So given the hash of x and also, as I said, hash of 2 to the m, which you do in advance at once, you do once in advance, you can get the hash of x prime, and then you keep moving until you get to the end of the text string t. Okay. Yeah. So what we'll have from this all these arguments, all these reasonings, is the Monte Carlo algorithm. Right? So it's going to have some error probability, but by our analysis, it's less than 1%. And the running time is going to be order m plus n, right? Because all these operations, this update takes just order 1 time. So to recap, right? So what we do, like the whole algorithm. So first we pick a random problem p from the range, like from 1 through this 200 mn log 200 mn. Right? So this, remember, it was our variable k in the analysis. So, and then again, like picking a random problem, you do this by picking a number from this range and then like keeping, when you repeat it until you get a number that's prom. And then you pre-compute so the pattern, the hash of the pattern, the hash of 2 to the m, and then the hash of the first substring of the text string that you want to test against. You check whether the hashes are equal or not. And then after that, for each step, you just do the update step, which you update the hash of from position from I to I plus m minus 1 to the next substring, that's position I plus 1 to I plus m. And for that, you only need to use the bit I plus m, and then the pre-computed hash of 2 to the m. And then you check whether a new hash is equal to the hash of the pattern p or not. Right. And yeah, so that's the recap. And this idea, is we just talk about the kind of one-dimensional string, but we can also generalize to more complicated pattern matching problems, right? Something like two-dimensional. So we'll see that in the tutorial. So for two-dimensional, right, you're checking, you have a, say, like there's a picture, and then you have a smaller picture. You want to check whether like this appears in larger picture or not. Then you can also use this idea, check whether this the same or not. And then if not, you like move 1% to the right, 1% to the right, and then sometimes you have to move down to the next row. But you can also use this this idea of rolling hash to do that. Okay, so that's yeah. By the way, mentioned the name fingerprinting at the beginning, but never talked about what yeah in the algorithm. Fingerprinting just refers to this hashing idea, right? So it's like the hash of a substring is its fingerprint, right? So instead of you have to compare the substrings themselves, you just compare their fingerprints, right? That's their hashes. So that's why this approach is known as fingerprinting. Yeah, and also yeah. So in the programming assignment, you're gonna do some variant of this problem where it's not just the strings themselves, but there can be some like missing characters, and then you want to check like what are the possible matches. So it's going to be a slight slight variant of what we have here. Okay, let me look at some questions. Yeah, okay, suppose we have to have match lowercase letters. Would it be 20 instead of 2 to the m? Would it be 26 to the m? Yeah, exactly. So if we have to say like match characters like lowercase letters like A to Z, then indeed like this at the beginning, remember I said this, we assume that we're dealing with a binary alphabet, but the idea works for any possible alphabet. So indeed, like you can look at this as a kind of base 26 number, and instead of 2 to the m, we're going to be dealing with 26 to the m. Okay, so question direct method. So the point is to move from hash to hash instead of element to element. Yeah, I mean, so that's one way to see it. Indeed, like we want to move from hash of string from 1 to m to the hash of the string from 2 to m plus 1 quickly, right, in constant time. Finding the next hash directly from the hash of the current element. Yeah, if by element you mean like a substring of length m, then yes, yeah, finding the hash directly indeed, instead of having to hash like beginning with the hash like the string 1 through m, then you hash the string from 2 to m plus 1. That's going to take like much more time. Right here, we only take constant time in order to go from hash of right, so in order to go from this x is string from 1 to m, right? And this s prime is string from 2 to m plus 1. And then this keeps working, and then you move one position to the right, you again apply this this process. Okay, so yeah, in the remaining time, I'm going to talk about another application of hashing, and that's in the context of streaming. So streaming is actually a big area in itself. The idea is that you have the input is so large that you cannot even hope to store in your on your local, say, like computer or hard drive, right? So this could be like IP addresses like coming in, or like other types of inputs that keep coming, and you don't want to store the whole thing, but still you want to get some important information from that. So it's kind of like you want to drink, but the input is so much that you cannot hope to drink or like keep everything. So what we want to do is we want to maintain a small data structure, right? That approximately answer like some relevant queries about the data stream that you've received. Okay, so in this model, so in the streaming model, what we have is a sequence of insertions or deletions from a large universe. I mean, so that should remind you of last lecture, right? This kind of sequence of insert deletes coming in from large universe that's like way too large for you to like store everything. So you have this these operations like add 3, add 1, add 7, right? That if you do the count, so here you have say like 1, 3, 7, right? You add 3, add 1, add 7, add 3 again, add 7 again, and then you delete 3, right? And add 1, delete 3, and delete 7. Right. So then you're going to end up with, you're interested in the frequencies, then you're going to end up with frequency of 3 being 0, frequency of 1 being 2, and then frequency of 7 being 1. Right. So maybe you're interested in these frequencies. These are in terms of could be like IP addresses, like that visit your website. I mean, in that case, that you're going to be dealing with only add, but then for some applications, maybe there's also a delete, and you want to know like what is the net count right, at the end, right, and or at any point of the stream. You want to answer the queries of what is the frequency of this element from the universe. So yeah, okay. So for as one variable, let this capital M be the sum of all the frequencies. So like the total net count at the end, like in this example, would be 3. Right. Okay. So what are we interested in? Right. We want to give a good estimate of these frequencies at the end of the stream. So yeah, well, we're fine with some error. Like we are fine with epsilon approximate. So that means that maybe the real answer is fi, but you find fi hat, and fi hat is something like fi plus some small epsilon times this parameter m. That's like the total frequency. So you're fine with some error, and yeah, if you see a problem like this where the universe is like way too large, but you want to just find some deal with a small subset of the universe and then answer some like insert delete queries, then you should automatically think of hashing, right? You're fine with some error. You want to do this quickly. So okay, like before hashing, like what could you hope to do? So this kind of similar to last lecture, right? And you could also you would hope to try to like create a direct access table, and why not make an array of all possible elements that can come in, and then an element come in, you just +1 at that position. Element is deleted, you just -1 at that position. I mean, so that yeah, you know by now that that's bad, because the space is going to be too much, right? It's order of size of the universe. And then the other other solution is that you could store the items as a sorted list, or as a balanced binary tree would also be fine. But then, like, okay, so space-wise it's better, but you only store the elements that come in, as opposed to like all elements that could potentially come in. But then the update times is not going to be order of 1, right? Because so you sort as could keep a sorted list or like a balanced binary tree. Like either way, the running time, the update time is going to be log of m, right? Log of the number of elements that are in the tree or in the array. So with hashing, we can do expected O1 time. So how does hashing work here? So with hashing, so again, we choose a hash function, and right, we want to keep the frequencies, right? We want to keep the frequencies of the elements that come in or go out or is deleted. So yeah, instead of keeping all possible positions, so this idea is like just pretty straightforward in that you build a hash function, and then you either you hash each element to a position. So certainly, like elements can collide, right? But then, like if element j comes in, then you increment the hash table at the position h of j, which is hash of j, and then if j is deleted, then we decrement the position hash table at position j, right? So h of j. And this size k is going to be chosen so that it's roughly, intuitively you could think of it as roughly the same as the number of elements that will come in. Right? So if some element is added, we hash it, then look at the position at that hash, and then increment. And similarly with the delete, we decrement. And then at the end of the stream, in order to estimate the frequency of element I, so we hash I, right, get h of I, and then we look at in the table at the position h of I, look at what's the frequency there, and then return that. Okay, so maybe let me ask you here. So okay, what is the answer? Can it be equal, higher, or lower than the actual answer, than the true frequency? Yeah. So indeed, it can be higher, right? It can never be lower, right? It can never be lower because assuming that the element's frequency never go below 0, right? So because what happens here is that elements can collide, right? And then when an element comes in, then it could be, it could be that, say, like I and j hash to the same position, right? So this is the hash table, and then I and j happen to be hashed to the same position. So when I comes in, like we plus 1, and then when j comes in, we again plus 1. So even though I and j are different elements, but if we are asked, like, what's the frequency of I now, we're going to return 2, right? Or what's the frequency of j now, we're going to return 2, right? Which is incorrect. That's an overestimate. But we're never going to underestimate, assuming that frequency of elements that never go below 0. So the answer could be correct, or it could be too high. So if h hash 1 and hash 2 equals hash 2 and add, we get the add 1 delete 2. So let's say we forbid that. We guarantee that the frequencies of elements like never go below 0 in the stream. Kind of this add and delete, it can never be that for some element kind of at some point there's more deletes than adds. So which I think makes sense, like for several applications, kind of that things will never leave like to more than they arrive. Okay, so yeah, we might get an overestimate, and it's a story that we've seen before already. If we choose a hash function, fix a hash function in advance, then right, if there's an adversary, then adversary could choose like everything to hash to the same position, and that would be really bad, right? So what we do is, of course, you use randomization. We randomize a hash function from a universal family in order to make sure that in expectation elements are not going to collide too much. Right? So what we now want to do is want to actually analyze how much they would collide, or like how much the estimate could be could be off, like could be an overestimate of the true frequency. So yeah, for the analysis, so what we're interested in is the position of the array at the hash of I, right? So what is it going to be at the end of the stream? So it's going to be the sum of the frequencies of all elements j, such that the hash of j is equal to the hash of I, right? So that's because they hash to the same position, so it's like the operations are performed on this position of the array. And as you can see, like if nothing else has the same position as I, then this is going to be the correct answer, right? The hash, this position of the array is going to keep track of the actual frequency of I. But if many things has the same position, then this could be a large overestimate of the true frequency of I. So we want to say that this is, yeah, it could be larger than f of I, the true frequency of I, but not by too much, right? Not by too much. And that's for that, yeah, we want to rely on the property of a universal hash function, which is that if a hash function is drawn from a universal family, then in expectation the number of collisions is not going to be too large, right? The expectation of like how this overestimates is not going to be more than like m over k. So k here is the size of the hash table which we can choose. And yeah, so why is that? Well, that's because if you look at each other element, right? So each other element is j, right? The probability that the hash of j is equal to hash of I, right? It's going to be no more than 1 over k, right? And this is by universality of the hash family. And so if you add, you think about the linearity of expectation, how much is j going to contribute to this overestimate? So it could be that if hash of j is equal to hash of I, then j will contribute f of j, right, the frequency of j, to the overestimate. Okay, because j is like treated in the same position as I. But if h of j is not equal to h of I, then j is going to contribute 0, right, to the overestimate. It's not going to hurt I in any way, because it's going to be dealt with in a different position of the array A, of the hash table A. Right, so but the probability that the bad event happens, so this is with probability at most 1 over k. Right, that's just by the line above. The probability that the hashes are like j and I hash the same position, that's at most 1 over k. So in expectation, j is going to contribute no more than fj times 1 over k, right, which is fj over k. And if we sum this up over all the other elements j different from I, what you're going to have is this term m over k, because m is like counting the total m is total frequency of all other all elements. And this m is sum of fj for all j. So because we have each j is going to contribute fj over k, and yeah, even I itself is going to contribute 0, so that's even better. But this term m is sum of all fj anyway. I mean, it's even if it is like less than I is fine, but for the analysis of I mean, m is defined to be sum of all frequencies, which is even a looser overestimate for us. So this saying that the overestimate is not going to be by more than m over k in expectation. Okay. So if we want the output to be in expectation and epsilon approximation, where epsilon is according to the previous slide, right? So here, yeah, we're fine with the kind of approximation being like fi like fi hat being at most fi plus epsilon times m. Yeah, and actually, because it's never going to be an underestimate. So here, like this never even going to happen, right? So what could happen is this overestimate here. So we have epsilon approximation if we choose k to be 1 over epsilon. Right? If you choose k to be 1 over epsilon, then this m over k is going to be m times epsilon, right? Which is overestimate this according to the formula that we kind of set out in advance. And if we choose this value of k, then the space, right, because hash table itself has size k, the space is going to be 1 over epsilon. Right? So the smaller epsilon is the better the approximation is going to be, but then the more we're going to have to pay in terms of space as well, right? Because space is order 1 over epsilon, and then we also need space to store the hash function. And the hash function, this is from now we don't have to rely on this rolling hash. We're not doing anything with rolling. This can be any universal hash family, like the one that we went over in the last lecture. For storing this hash function is going to be order of log u, right, the size of the universe, times log of k. So the size of the hash table. This hash function is, remember, it's hashing from the universe to a table of size k. Right? We store the matrix. Remember this matrix A from last lecture, kind of that you multiply this matrix with an element of u, and then you get the vector of size k. So the hash function is this matrix itself, which the number of bits is going to be log u times log k. Okay, so yeah, this gives you the analysis of this algorithm, which uses the hash table, so it can overestimate, but not by too much. And actually, like this, you can see that this is the bound on the expected error, right? This expectation of this overestimate is not more than by m over k. A stronger guarantee of this form is going to be that instead of bound on the expected error, we want to guarantee low error with high probability. Right? So instead of saying that the expectation is no more than this, we want to say something like, let's say, the probability that this hash function or this overestimate is probability that this term is more than m over k is small. Let's say where small can mean like but whatever you want can be like maybe 1%, something like this. This will be a stronger type of guarantee than saying that just expectation is not more than m over k, because expectation not more than m over k maybe it could be like, with probability half it's correct. It's like the not overestimate. Maybe with the other probability of half it's like 2m over k, something like this. Then the expectation would still be m over k, but that could be kind of bad. Like with probability half, you're getting kind of a bad overestimate. But yeah, this analysis here just gives you an expectation, and in order to get the kind of low, like high probability guarantee, what you can do is instead of using just one hash table, I mean, so this goes back to the idea that some of you pointed out in the for string matching, is that instead of using just one hash function, right, why not try like several different things? And indeed, like this is a good idea. So you can try a different hash tables instead of using one, because using one hash table, you just construct one hash function, maybe you still get unlucky, right? I mean, even though like the probability of getting unlucky is small, but maybe like you get unlucky there. So why not just like use different ones? And for each one, I mean, you can remember, you can get overestimate, but you can never get underestimate, right? So maybe the first hash table tells you that f of I is 6. So true f of I is either 6 or smaller. Maybe the second one tells you like f of I is 4. Maybe the third one tells you f of I is 4 again. Then what you can do is the answer is going to be no more than the minimum among these numbers, because all these numbers are either correct or an overestimate. So you can take the minimum number, and then here, like say, you return 4 as the frequency of I that you think the frequency is 4. So return 4, and then like this because you're using several hash functions, the probability that you're correct, and the probability that this is not an overestimate is going to be larger. This gives you a bound, high probability bound on the overestimate. And the analysis of this this is kind of beyond this module. But if you're interested, we have a whole module on randomized algorithm that's 5330. Okay, so yeah, that's it for this lecture. So we end a bit early, but yeah, as I said at the beginning, kind of yeah, there will be quite a few things, components of this module over the research week. So we'll gradually send out the email announcements for that. And when we come back, we have the midterm. So make sure you read the instructions carefully about setting things up. Okay, then have a good recess week. Hope you get some rest and come back ready for the midterm and the second half of the module. All right, I'll stick around for questions.
Hi, Prof. Can I ask a question?
Yeah.
So most of these algorithms that we analyze, like there is a chance that there errors will occur, correct? But the chance is very low.
Yeah, I mean there's a chance that they're wrong.
Like the for example, the finding whether this subscript string is present in the main string is like there's a chance that it might give a wrong result, but that chance is minimized to a very small amount.
Right. Yeah. And then the key for this, like how much you're willing to accommodate this chance of being wrong, right? I mean, here is if you increase the k quantity, 200 times log 200, and if you want the probability to be even lower, you can increase this quantity, that the probability is going to be lower.
I see. Okay, thanks.
Needed someone coming out with the comments. So you want to be sure, kind of like when the algorithm says that there's a match, then you can indeed like spend the time checking whether this match is really correct or not. Then you're going to have an algorithm that's always correct, but at the expense of higher running time.
I see. Okay, thank you.
Okay, so what does a hash function derived from a high k look like? So it looks exactly like the same, I mean, as before. So this k is just the parameter, right? Then remember we choose a prime number p from the range of 1 through k, and the hash function you just take modulo p. So what the hash function looks like doesn't really depend on k. Just that if k is larger, then you have more prime numbers p to pick from. And it could be a large prime number p, which takes you more time. Okay, in the direct method, how can you explain slides 17 through 19 again using specific? Oh, sorry. So I don't have the slide numbers. Actually, can you tell me which slides? Okay, rolling hash. Yeah, sure. So so here, right? Suppose let's say m is maybe m is 4. Then let's say string s. Yeah, let's say the first 5 positions of the strings are like t, maybe the text string t, which is maybe it starts with 11001 something. So at the beginning, right, we're going to check whether the first substring, right, the first 4 positions, matches with the pattern P or not. Right, we want to compute the hash of x. So first x is what? X is 1100, right? So if you interpret that as a binary number, that's going to be 2 to the 1 times 2 to the 3. Plus 1 times 2 to the 2 plus 0 times 2 to the 1 plus 0 times 2 to the 0, which is yeah, I mean, you can compute this to be, then this would be like 12, but it doesn't matter. But then S prime is what? S prime is moved to the right by 1 position, right? It's now the string that you're interested in is 1001. So it's going to be 1, yeah, it's going to be like 1 times 2 to the 3 plus, yeah, now it's going to be 0, 0, and then 1. But the point here is that you can see that x, because x and s prime are similar, right? They overlap in 3 of the 4 positions. So you can get from s to s prime by just moving by 1 position. You can see that this, let me come right in red. So this part here, similar to this part here, right? It's 100. It's just shifted by 1 position. So that's why to get s prime from x, you can use this formula here. So s prime equals 2 times s, right? Because if you multiply x by 2, what that's going to do is this s, like this becomes power 4, it becomes power 3, power 2, power 1. And now the 2 red boxes are the same. Yeah, the top one and the bottom one are the same. So in order to get the s prime from x, now we can just subtract this term, like the green circle here, like 1 times 2 to the 4, and then plus this term here, right, 1 times 2 to the 0. So that's exactly what this formula is saying, right? Getting from x to s prime. And then in the next slide, that's saying that, okay, this is getting from s to s prime, but what about getting from the hash of x to hash of s prime? We can also do that quickly because hashes can distribute into addition and multiplication. That's why getting hash of x to hash x prime can be done using just this formula. Just apply the hashes.